Assalamu alaikum friends. Today we are going to learn about Jacobian matrix. Well, Jacobian matrix is a very important and a useful matrix that organizes partial derivatives of a vector function. Partial derivatives are used for so many things and we want to organize them. So the term Jacobian is actually the determinant of the Jacobian matrix. These Jacobian matrices are very helpful in doing transformation of coordinates. I'm going to make my point clear by taking an example. For example, this capital F is defining a vector function which comprises of actually two sub-functions, f1 and f2. Both of these sub-functions are defined in two variables, x and y. So if I want to write down a Jacobian matrix for this vector function f, then it should look like something like this. The partial derivative of this first function with respect to x, the partial derivative of this first function with respect to y. And in the second row, partial derivative of the second function with respect to x and partial derivative of the second function with respect to y. If I make it a little bit generalized and I say that if I have a vector function that is not only having these two functions, it is having n number of sub-functions, and these functions are not only defined in two variables, they are defined in n number of variables, then the Jacobian matrix should look like the first row will contain the partial derivative of the first function with respect to all the variables in which that function is defined. For example, it is defined in x1, x2, x3, x4 till xn. The second row of the Jacobian matrix will contain the partial derivatives of the second function with respect to all the variables in which that second function is defined. And similarly, I will go on till the partial derivative of the nth subfunction. And the partial derivative of that nth function will be calculated in all the variables in which it is defined. So that will be a huge, large Jacobian matrix. If, of course, it is a vector function that is defined in only two functions and they are only f1 and f2, so it will have two rows. And if these functions are defined in only two variables, then it will have only two columns. But for example, if it is defined in x, y and z, then of course there will be three columns, one for x, one for y and one for z. So basically the number of columns are determined with the help of number of variables in which the functions are defined, and the number of rows of the Jacobian matrix are dependent on the number of subfunctions that exist inside that vector function. Okay, now let's take an example. We have a vector function that is defined into these two sub-equations or sub-functions. I want to find out the Jacobian. So Jacobian will be the partial derivative of this first function with respect to x, and then the partial derivative of this first function with respect to y. Remember, there are no second order derivatives. We solved Hessian matrix in my previous video. There were second order derivatives, but right now there are no second order derivatives. They are just first order derivatives, but yes, there are more than one functions. So this is the very important difference between Hessian matrix and a Jacobian matrix. Hessian matrix may contain second order derivatives, but the Jacobian matrix only contain first order partial derivatives, but for a vector function, and a vector function comprises of many subfunctions. Alright, so you have to remember this thing. Okay, so this row is dedicated to this first function and the second row is dedicated to this second function. So first term is defining the partial derivative of this function with respect to x, and the second column is representing the partial derivative of this function with respect to y. So if you calculate the partial derivative of this function with respect to x, for x you will get 1 and for sine of y you will get 0 because it has no x term. Okay. And if I calculate the partial derivative of this function with respect to y, then I will get 0 for this x because it has no y, and for sine of y I will get cos of y. Okay, let's go to the second row. The partial derivative of this second function with respect to x. So for y you get a 0, and for sine of x you get cos of x. And when I calculate the partial derivative of this function with respect to y, for this y I get 1, and for sine of x I get 0. So this is my Jacobian matrix. If you want to find out the Jacobian for this matrix, the Jacobian is determinant of the Jacobian matrix. So if you want to find out the Jacobian, then you have to multiply these terms minus multiply these terms. So cos square will be the Jacobian. Okay. If I want to evaluate this Jacobian matrix at a point, for example, I have this point in my image, this point, and I want to evaluate it on this point where x is -2 and y is 1. Then I place the value of y as 1 and the value of x is placed as -2. So it will come out to be 1 minus 0.42, 0.54 and 1. So if you actually want to evaluate it in the terms of the vector functions, because this was your vector function, so it is comprising of some vectors. So if you draw two vectors out of this point, so one is this red vector and one is this green vector, and both these vectors have some x components and y components. So for this red vector you can actually see that this component this component which is along x-axis, it is, you can see that it is large, it is almost equal to this vector itself. That is why we are having a 1 over here, and the y component of this vector is small and it is towards the downside, it is pointing towards the downside. That is why this component is equal to 0.54.